are all going good. So in this video lecture, we'll be starting with the fourth module of EC405 Optical Communication in KTU for Electronics and Communication Engineering. So these are the syllabus for your fourth module. We'll be dealing with each of these: digital transmission systems, design of IMDD links, power and rise time budgets, coherent systems, sensitivity of a coherent receiver, comparison with IMDD systems, introduction to soliton transmission, soliton links using optical amplifiers, GH effect, soliton-soliton interaction, amplifier gain fluctuations, and finally design and guidelines of soliton-based links. So these are the few questions that has been asked in the last university examinations. You can have a look. So first topic that we'll be discussing is a digital transmission system. So as the name indicates, a digital transmission system, the signal is in the digital form. So the digital signals are not continuously varying signals. These are signals which has a discrete value, mainly two values of some physical quantity, and the signal will be varying between these two values. In binary denotations, it is either 0 and 1. So the signal can be either on upper level, then it is 1. If it is on the lower level, it is 0. So basically that is for the binary case. If it is not binary, there will be some physical quantities for higher value and the low value, and the signal will be toggling between these two values. So in analog communication, you will be having a continuously varying signal, and these continuously varying signal can be electric signal or voltage signal, and that is being transmitted through the copper cables. We have mostly copper cables are used for transmission of analog signals. So for transmission of digital signals, we can either use a wireless technology or using optical fiber communication. So these optical signals, when compared to when comparing or when putting in the digital domains, these optical signals will be having optical intensities, and these optical intensities will be toggling between these two values, a higher value and a lower value, and these optical intensity variation can be modulated and then can be transmitted through a communication medium. Similarly, at the receiver side, this optical intensity variation should be detected by an optical receiver, and the corresponding decoding has to be done, and the signal can be extracted. So we have the electric input pulses that is given to the LED or the laser transmitter. The LED or the laser transmitter can modulate this electric pulses, which is binary input, which is toggling between the value of 1 and 0. So this can be internally modulated or externally modulated. Some transistors modulate internally, so this can be modulated and then converted to optical signal, and that is being transmitted through an optical fiber. Similarly, at the receiver, it is detected by a photodiode. Any type of photodiode we can use. We can use either pen photodiode or avalanche photodiode, and correspondingly the electric signal is being obtained using the amplifiers and the filter. We can if you can either amplify the signal, because on transmission we can have various losses. Because of it, the amplitude of the signal can vary, so you can compensate for that losses and filtering out the unwanted signal. The unwanted maybe during the transmission, unwanted signals are picked up, so that unwanted signals can be filtered out, and we can have the output. So the next topic for discussion is intensity modulated or direct detection system, or IMDD system. So intensity modulated and direct detection. So these are two processes that are happening at two sides of the optical communication system. As I've already told you, whenever we have a signal and we have to be transmitted, when you have a signal and that has to be transmitted to a receiver, from the transmitter to a receiver, the signal has to be modulated. You know why the signal has to be modulated? Because we have already learned that the basics in our analog communication. Every signal has to be modulated so that it reaches the receiver end. So is the case of optics also. In optics also, we need to modulate your signal. So the type of modulation that is being used here is intensity modulation. And the type of detection, demodulation, that we use at the receiver end is direct detection. So the system that uses intensity modulation at the transmitter side and direct detection at the receiver side is known as IMDD system, that is intensity modulated direct detection system. So what are the advantages of a intensity modulated direct detection system? You know, so in intensity modulation is nothing but the optical power or optical intensity is varied depending upon the modulating signal. Okay, and these optical power variation of the variation in intensity of the optical power can be easily detected by the direct detection system. In the direct detection system, you have a optical detector. So, in intensity modulated direct detection system, the intensity of the power of the light beam from either a laser or a light emitting diode is modulated by the information bits, and we do not require any phase information here. Only the intensity variation is what you require. You don't require any phase variation. So, due to this nature, you don't require a local oscillator in IMDD system. So, this eases out a great amount of cost in the system. So that is all about IMDD system. So every system has certain shortcomings. So one of the shortcomings of intensity modulated direct detection system is its multipath effect. What is this multipath effect? Is that the cause of multipath effect can be mentioned in three. One is that this light is reflected at multiple occasions at multiple surroundings. So when the light is being at the receiver end, there are chances that it get lost. Then other thing is that the modulation bandwidth of LED has limitation. As we all know, the modulation bandwidth of LED is around 100 megahertz. So if the bandwidth of the signal is exceeding this 100 megahertz of the LED, there can be losses or the multipath effect. And thirdly, these light components travel in different wavelengths, propagate through different paths, which can cause multipath effect. So all these effective means of mitigating the multipath effects are necessary. OFDM, if you are using orthogonal frequency division multiple access technique, multipath effect can be reduced to a considerable amount. So you can see the block diagram of intensity modulated direct detection system. You have a transmitter side and you have a receiver side, and the communication medium or the channel is an optical fiber. So an optical source can be either a laser or a LED, and this is being modulated through an optical modulator, and the information is given. You have a optical signal and you have a information source, as I've already mentioned. These the intensity of the optical source or the LED is varied with respect to the information signal, and that is being transmitted through an optical fiber. So in the transmitter side, it is always there are two processes by which the modulation can be done. It can be external modulation or internal modulation. That is, inside the optical sources itself, it can modulate the signal. So or it can do it with another external circuitry. So it can be external modulation or internal modulation. So that is being transmitted. After modulation, the signal is being transmitted to a fiber. At the receiver, you have the photodetector for naturally detecting the optical signal and converting it to the electric signal, and then amplifier equalizer, that is the signal conditioning circuits. And you have a decision device have a data recovery and the clock recovery units, and the information is finally received. So the next topic is link design. So when you're considering the link design, point-to-point link is the simplest form of a light wave system. In point-to-point link, you have a transmitter, you have a receiver, and you have a communicating channel that is optical fiber. So that is a simple point-to-point link form of light wave system. So, there is another factor associated with the point-to-point link system is the link length. Depending upon the link length, you can have short-haul communication system and you have long-haul communication system. So, when this link length exceeds a particular limit, like 10 to 100 kilometers, we require repeaters or optical amplifiers to compensate for the losses that happens in the optical communication system. And this link length depends upon the bit rate, and the bit rate depends upon the wavelength at which the point-to-point link communication system is working. So, in order for criteria, when you're defining a criteria to measure the performance of a point-to-point link communication system, the product of bit rate and length is a measure. And this bit rate, since the bit rate depends upon operating wavelength, so the product of bit rate and the length BL will depend upon operating wavelength. And because of this bit rate has a dependence on dispersion, and length has a dependence on attenuation. Because of the bit rate is a factor for causing dispersion in a point-to-point link. Similarly, link length is another factor that accounts for attenuation in the point-to-point link communication system. So the two criteria that are related to the transmission parameter of optical fiber are fiber attenuation and fiber dispersion. As I already mentioned in the previous slide, the length L is related to attenuation and the bit rate is linked to dispersion. And the calculation of this the distance calculation on the length calculation is referred to as power budget, and similarly the bit rate calculation is referred to as rise time budget. We'll go in detail for these two topics, power budget and rise time budget, in the next videos. So this is a basic point-to-point link communication system. We've already seen this block diagram in our first module. You have an information source, you have optical transmitter, you have an optical fiber, you have an optical receiver, and you have a user. So the key parameters to analyze the link is the transmission distance, what is the data rate at the channel bandwidth that can be put in this point-to-point link communication system, and what is the bit error rate. Analyzing these three parameters, we can analyze the point-to-point link communication optical fiber communication system. And nextly, the design engineer, when he is designing a point-to-point link optical communication system, the factors that he needs to consider are you need to consider what are the various aspects in choosing the optical transmitter, what are the various aspects that you need to follow when choosing the receiver, and similarly what are the various aspects that he need to look after when he is choosing the optical fiber. We've already discussed all these 3 points in detail in our first module. So if you have any doubts regarding those criterias, please refer the first module.